You guys know any of the basic gas laws at all?
So these are the laws defining the behavior of gas.
PVT equals P2 V2 over T2?
What?
Yeah.
Okay, wait.
Yeah.
P1 V1 over T1 equals P2 V2 over
You know what it's
T2.
called?
I don't remember. I don't need to remember that till later in the year.
So
Chemistry,
this is,
gas laws.
This is the defining overall gas law.
It's called the
sort of-
combined gas law.
Ah, yes.
And this stems from simpler laws that Nathan will do video on.
Gas law.
That's the opposite of
Okay, I'm going to sit right there, so you
Alright.
might not want to sit there.
We're not starting with that. We're starting with the components of that, which are. Has anybody heard boil before?
BOIL.
Haven't you taken this class?
Yes.
Have any of you guys heard of boil before?
He said
Boil.
like Moore's law, Charles law.
Okay, so boil has a gas law.
Boiling red.
Boil it.
What?
Does that mean
I would prefer a darker color if you don't mind.
How's there a darker
That's
color
black.
than black?
Then push down more.
Thicker and more visible.
I don't know.
I know, Rishi.
I go back and watch them so I can take notes. Ha! Ha ha!
Can you see that?
I can see that. Rachel watches these.
Alright.
Rachel says she watches these.
Okay, yeah, Rachel
So-
says she watches these.
Boil has a gas law.
Rachel and Peyton,
That
if you watch
said-
this, let us know.
That says pressure times volume is equal to a constant number. Basically,
What does that mean?
your pressure,
So when in the constant temperature,
right,
pressure and volume are
equals
constant. The product of those are constant.
pressure.
Pressure of what? Volume of what? Nathan,
You asked so many questions. I know you.
I don't understand.
Okay. So in a gas situation, when you've got
What's a gas situation?
when you let me finish.
When you eat too much Mexican,
Let's say this is a space, okay? And you've got little gas particles flying around
Can
in
you
here.
push down harder?
Shut up. There are a bunch of little gas particles, okay, guys? And they're in a space. The pressure of the gas particles is inversely. Give me a second. Is inversely proportional to the volume of the gas particles. So, if you add more pressure, that would
make it shrink.
it would make it shrink. Does that make sense? So, more pressure.
How do you get some more pressure?
If you put weights on here, if you put weights on top of this box
You
here,
put weights on your gas.
if you
I'm
put
trying to
weights,
understand. No, these are questions they would be asking if they were
Nathan,
if they were more.
Try this. You're holding a balloon, and then you let it go.
Go,
And it
go.
floats, and the pressure decreases. What happens?
I get what you're saying, but that's not the best example.
So,
I'm gonna go with this
yeah.
example.
Okay.
All right. So if you had this box, and you put pressure on top of the box, then it would cause the box to shrink inside. And that's why if you have more pressure, then you will have less volume. And
So you have a plunger, and you're gonna push down on it. So
by
when you
you apply pressure down on the plunger. Does that make sense? So you're applying pressure to the system, which would increase the pressure of the system and decrease the volume of the system.
I have a question. What does it mean? What does pressure actually mean, though? Like qualitatively, not quantitatively.
Force per area.
Force per area. But if I have a sample of gas, what does it mean to have pressure?
Jack, you're going to go over that, right, in molecular explanation? All right, so we're going to go over that later.
But essentially, it's the force. It's the total force in a unit of area.
So by applying pressure down, you're applying force over that area. That's hard to explain, guys. You're making this hard to explain for me.
No, I'm asking questions that they would ask if they were a little more vocal right there.
Well,
Right?
I have a question.
Ask your question then.
Wait, so when you add pressure,
Yes.
and the volume decreases, is there like a specific scale? Like, are they proportional?
They are directly proportional.
Okay.
So
if you have
so
one-
if you increase volume, let's say we double the volume and we're just letting it expand, we could do that by cutting the pressure in half.
They're inversely. Yeah, you're right. They're
So if I
inversely
wanted to
proportional.
triple it, I'd do it by scale of 1/3 and vice versa.
So
Okay.
2 times the pressure would result in half the volume. So that way it would be 2 times half equals 1 times 1. Does that make sense?
Can I do a sample problem?
The idea is that your equation represented PV equals PV. So your system in the beginning, with that certain pressure and that certain volume, is equal to your system after whatever change it undergoes. So Nathan gave the example that you increase pressure. So when you increase pressure, what happens?
You lose volume.
You decrease volume.
Yeah.
When you increase volume, you... Right. Assuming what? What does Nathan tell you about Boyle's law?
There is an assumption that's made. That
You have to make one major assumption before you can say any of that.
Temperature is constant.
Temperature is constant. See? And the way you remember it is Boyle's law. What do you do if you boil something?
Add heat.
You add heat. But it's tricky because Boyle says there's no heat.
no change.
So, so you remember it by
This is
thinking
not very
the opposite of what happens.
Exactly.
So
That's how
you
I
know
do it.
Boyle's tries to trick you. So when you add heat, nothing happens. That doesn't apply to Boyle's law. Other things happen other than this.
So another way you can look at this is by making a pressure volume. Wow, this is terrible. You want to make a
Yeah.
graph for me?
So if you were to have a pressure versus volume graph on a measurement of just any particular gas, pretty sure it's volume on the bottom. Osman, you left. Amber, can you confirm this? Shrug. Okay.
It's pressure on the bottom.
Alrighty.
Yeah.
Pressure on the bottom.
Does it really matter that pressure goes in the
yes.
bottom?
Well, it doesn't here, but it does later for different.
So let's say we were to graph an inverse relationship, looks like that. Then at any point here, if we wanted to change it, keeping the temperature constant, this point would move, say, to here. And it moves only on this line because pressure times volume remains constant. This is called an isothermic change.
So like this value right here times that value is equal to the same thing as this value times that value.
Okay, wait, can I really quickly jump in once again? Okay. Sorry, it was all okay. So, alright, so they said pressure times volume equals a constant value, right? What do you want to give the constant value? Give me a number.
I was about to do this.
Okay, let's say the number is K. Okay.
Great.
So, right here you have pressure in your P. Like, so, if you have a graph, right, like a regular graph that you guys do in math, the y-axis is the dependent variable, right? The y is the dependent variable, and x is the independent variable, okay? Over here, your independent variable is pressure, and your dependent variable is volume, or vice versa, because it doesn't really matter. It just depends on how you view the graph, right?
Yeah, it depends on what effect you're doing.
If you're looking at it sideways, it's going to be the opposite. Okay, so the idea is that if I say that V equals K over P, right?
Where K is just some constant.
K is any number, it could be 1. Let's say K is 1, right? And let's rewrite this.
Let's say it's 1 Pascal times meter cubed.
Yeah, so it's Y equals 1 over X. It's the same relationship, right? So
Yeah.
if you guys remember from Algebra 2 or Algebra 1, I don't remember exactly when, your parent function Y equals 1 over X looks like that in the first quadrant, right?
Yeah.
Which is why your pressure and volume graph looks like that. Okay? So you have an inverse relationship due to the fact that the product of pressure and volume is always going to be constant. Okay? And so as you change one, the other will change in the opposite fashion, right? So if you increase volume, you decrease pressure, so on and so forth. So this is like a big mess. The main thing to get, that the product of pressure and volume is a constant number. And that, yeah.
Okay. Are we done with Boyle's law?
Let's do a sample problem. So, let's say that we have a volume of. And I need to clear stuff off.
Don't do
Osman, can you find me what?
wait, Robert, where's your eraser?
So, if let's say we have a volume, initial volume of say 4 liters, and we have an initial pressure of 50 pascals. Okay? And then we're going to try to force that into a container of 7 liters. What is going to be the new pressure? So get out paper and pencil and work out what will the new pressure be using Boyle's law, assuming constant temperature. So it's like you take a tank of compressed air and you're putting it into a balloon that's 7 liters big.
28.57.
Okay? And how did you find that? You're correct.
So I multiplied the volume times the pressure, so you get overall 200,
Okay?
and then you divide that by 7 liters to get 28.571.
0.7 you said?
Yeah.
Right. Does anyone not understand how I got to that? Brilliant. Nathan, the floor is yours. Should I erase Boyle's?
Yeah.
People watching video, pause, make sure you have everything. Question.
You said isothermic something.
Oh, yeah.
Back then. What does that exactly mean?
Okay, so isothermic. I'll cover this while Nathan has his mouth full. Isothermic. The iso means constant or unchanging, and thermic refers to heat or temperature. So the idea is temperature remains constant. So if we were to change the temperature, then the whole graph would shift kind of like that. So you'd get the whole curve moving. Has anyone ever seen like a weather diagram where they have, say, a cold front moving in and there's weird curvy black lines going throughout? Those are isobaric lines. Those refer to pressure, constant pressure.
Realize if you isobaric, right? So a bar or baric, a bar is a unit of pressure, right? And hey, if you're stuck, if you see isobaric and you know it has something to do with gases, get out your UIL sheet right here, and under, let's say, pressure.
Under constants, there should be a relationship between
They don't.
bars, milliliters,
They
mercury.
don't do bars, but I guess just keep in mind that a barometer measures pressure, bar is a unit of pressure,
Isobaric is constant.
isobaric is pressure.
And has anyone ever seen a is it topographical map?
Yeah.
So what do those lines mean? What does walking along a line mean?
Change in elevation.
Right. It measures a constant elevation. So if you cross lines, you're changing your elevation. If you stay on a line, you're at a constant elevation. And those are iso-elevated, or isotropic, I think. Isotropic lines for constant elevation. Is that right? Isotopic. Thank you. So the idea is iso means same. Thermic refers to temperature or heat. Okay.
You got that right.
So sorry, now pause the video.
They probably paused it. But got to this. All right.
So far, what values have we related with gases? We talked about gases, right?
So what
Gas
things
and
that we measure?
What have we
have
talked about with gases so far? What about gases? Their
Pressure and volume.
pressure and volume. And kind of temperature, because they're at a constant temperature, right? Okay. So if you're taking notes, keep like a running list, I guess, so far. Pressure, volume, temperature. Or if you keep notes in your head, whatever you're doing. Watch the monkey. Nate, watch the monkey.
Okay. Watch.
This is inconvenient. I took pictures of it. Can we just recreate this after?
Yeah.
I took a picture too, so we're good.
So erase back to here, Nathan.
Sure.
Yes.
Won't let
No.
All right. So our next gas law is also pretty. It's actually a lot like that first one. It's Charles's. Charles.
And then there's Sancho's law governing burritos.
Charles's law. We don't have a cute thing like Boyle heat thing for that, but Charles's law.
Actually, I do.
He do?
First do it. First write down.
Okay.
That's a
I feel it's gonna be completely just like random connections.